On the morning of February 25th, 2025, a small team of engineers at NASA's Jet Propulsion Laboratory sent a command across more than 15 billion miles of empty space, and something inside Voyager 1 went quiet forever. It was not a dramatic failure. There was no warning light, no alarm, no visible sign that anything had changed at all. It was simply a switch turned off on purpose by the people who built and still fly the oldest functioning spacecraft in human history. The instrument that fell silent that day was called the Cosmic Ray Subsystem, a set of 3 tiny telescopes that had been quietly measuring high-energy radiation since before most of the engineers who shut it down were even born. And now, in 2026, its identical twin aboard Voyager 2 is scheduled to receive the exact same command. When it does, humanity will lose its last active window into cosmic radiation from a region of the universe no other spacecraft has ever reached. And once that switch is flipped, there's almost no chance it will ever come back on. This is the story of why NASA is being forced to make that decision, what the instrument being switched off actually does, and why the people who run the Voyager mission describe every single day of its remaining life as something that could be its last. To understand why this moment matters, you have to go back to 1977 when 2 nearly identical spacecraft left Earth just 16 days apart. Voyager 2 launched first on August 20th, followed by Voyager 1 on September 5th, which took a faster, more direct route, and ended up arriving at Jupiter first, despite launching second. Both spacecraft were built for a single specific purpose: to take advantage of a rare alignment of the outer planets that only happens once every 176 years, and use it to fly past Jupiter, Saturn, Uranus, and Neptune in a single continuous mission that NASA called the Grand Tour. Nobody involved in building them expected either spacecraft to still be operating in 2026. They were designed for a mission expected to last around 4 years. Instead, both spacecraft kept going. Voyager 2 became the only spacecraft in history to fly past all 4 of the solar system's giant planets, visiting Uranus in 1986 and Neptune in 1989, encounters that to this day remain our only close-up look at either world. Voyager 1 took a different path, using a gravitational slingshot at Saturn to send it flying up and out of the plane of the planets entirely, sacrificing any chance of reaching Uranus or Neptune in exchange for a direct trajectory toward the edge of the solar system. That decision, made decades ago, is part of why Voyager 1 now sits farther from Earth than any other human-made object, at a distance of more than 15 billion miles, while Voyager 2 trails behind at just over 13 billion. Both spacecraft carried an identical set of 10 scientific instruments, including 3 tiny telescopes bundled together into something called the Cosmic Ray Subsystem, or CRS for short. Its job was straightforward in principle, even if the physics behind it is not. Cosmic rays are extremely high-energy particles, mostly protons, that come from 2 very different places. Some are thrown outward by the sun during solar storms, and others come from far outside the solar system entirely, accelerated to nearly the speed of light by exploding stars and other violent events scattered across the galaxy. The Cosmic Ray Subsystem measured the energy and the flow, or flux, of these particles as they streamed past the spacecraft, allowing scientists back on Earth to tell the difference between particles that originated nearby, from our own sun, and particles that had traveled from somewhere else in the Milky Way entirely. For most of the mission, this data was useful but not headline-grabbing. It helped scientists understand the radiation environment around Jupiter and Saturn during the original planetary flybys. But everything changed once both spacecraft began approaching the edge of the heliosphere, the enormous bubble of solar wind and magnetic field that surrounds our entire solar system and is inflated outward by the sun. As Voyager 1 approached that boundary, something remarkable started showing up in the Cosmic Ray Subsystem's data. The number of low-energy particles coming from inside the heliosphere from our own sun began dropping sharply, while the number of high-energy cosmic rays arriving from the wider galaxy spiked upward at almost the exact same time. That specific pattern, that exact signature, is what allowed scientists to confidently determine that on August 25th, 2012, Voyager 1 had crossed the heliopause and become the first human-made object in history to enter interstellar space. Without the Cosmic Ray Subsystem's data, confirming that historic crossing would have been far harder and far less certain. Voyager 2 followed a different path through a different region of the heliosphere, and its own Cosmic Ray Subsystem played the same essential role years later, helping confirm its own heliopause crossing on November 5th, 2018. 2 identical instruments on 2 separate spacecraft, both used to mark one of the most significant milestones in the entire history of space exploration. And now, one of those 2 instruments is already gone, and the second is scheduled to follow. The reason comes down to something almost embarrassingly simple: electricity. Neither Voyager carries solar panels, because sunlight at their current distance is far too weak to generate any meaningful power. Instead, both spacecraft rely on something called a radioisotope thermoelectric generator, a device that converts the heat produced by the natural radioactive decay of plutonium-238 into usable electricity. It is an elegant solution for deep space, because it requires no moving parts and no exposure to sunlight, but it comes with an unavoidable, physically unchangeable downside. Plutonium-238 decays at a fixed, predictable rate, and as it decays, it produces less heat, and therefore less electricity year after year, with absolutely no way to reverse or pause that process. NASA engineers have calculated that each Voyager spacecraft loses approximately 4 watts of available electrical power every single year. It began with roughly 470 watts available at launch in 1977. Today, there is only a small fraction of that left. 4 watts might sound trivial. A single household light bulb can draw more power than that. But on a spacecraft that has already been stripped down to its most essential systems, with no factory, no backup parts, and no possibility of repair, 4 watts is the difference between running an instrument and losing it forever. Every heater, every science instrument, every transmitter, and every onboard computer draws from the exact same shrinking pool of electricity, and there's no way to manufacture more. For years, NASA managed this slow, irreversible decline by shutting down systems that were, relatively speaking, less essential. Cameras that had photographed Jupiter's storms, Saturn's rings, and the iconic pale blue dot image of Earth were switched off decades ago to save power, since neither spacecraft has photographed anything since leaving the outer planets behind. Certain heaters were disabled, some backup systems were sacrificed outright. But by 2024 and 2025, the easy options had run out, and NASA found itself forced into a much harder set of decisions, not which spare systems to sacrifice, but which working science instruments to permanently silence. The sequence began in earnest in September 2024, when Voyager 2's plasma science instrument was switched off. In February 2025, engineers shut down Voyager 1's Cosmic Ray Subsystem, the very instrument that had helped confirm humanity's first crossing into interstellar space. 1 month later, in March 2025, Voyager 2's low-energy charged particle instrument went dark as well. In April 2026, Voyager 1 lost its own low-energy charged particle instrument too. Each of these decisions followed the same brutal logic. Suzanne Dodd, the Voyager project manager at NASA's Jet Propulsion Laboratory, put it plainly in a statement explaining the shutdowns. If the team did not turn off an instrument on each spacecraft, both Voyagers would likely have had only a few more months of power left before mission engineers would have had to declare the entire mission over. That leaves Voyager 2's Cosmic Ray Subsystem as the next instrument scheduled for shutdown, sometime later in 2026. When that command is finally sent, Voyager 2 will join Voyager 1 in operating with only 2 remaining instruments: a magnetometer, which measures the strength and direction of the magnetic field surrounding the spacecraft, and a plasma wave subsystem, which detects oscillations in the extremely thin charged particles that make up interstellar space. Every other instrument on both spacecraft, 10 in total combined, will have gone silent, one at a time, over the course of just a few short years. It is worth pausing to understand exactly what will be lost the moment Voyager 2's Cosmic Ray Subsystem goes dark, because it is not simply a matter of losing a redundant backup. Voyager 2 remains, to this day, the only spacecraft in history to have flown past all 4 giant outer planets, and it is one of only 2 spacecraft that has ever operated beyond the edge of the solar system, in the region between the stars. No other functioning mission anywhere in the solar system is positioned to measure cosmic ray flux from that specific location, in that specific direction, at all. Ground-based observatories and telescopes can study cosmic radiation indirectly, but nothing can physically sample the particles themselves the way Voyager 2's instrument has been doing continuously for nearly half a century. Once that instrument is switched off, an entire class of direct real-time measurements from interstellar space will simply stop, with no scheduled replacement mission anywhere close to reaching a comparable distance for decades to come. There is also a quieter, more technical reason this particular shutdown carries extra risk. Unlike some of the earlier instrument shutdowns, which mostly involved switching off a single, self-contained device, the Cosmic Ray Subsystem and instruments like it are wired into a shared electrical and thermal system alongside the equipment NASA actually wants to keep running. Powering down one component can shift heat distribution elsewhere on the spacecraft, alter voltage behavior in unexpected ways, or interact with backup systems that have not been touched in years. Every single command sent to either Voyager has to be tested, modeled, and reviewed carefully in advance, because there is no way to physically inspect the spacecraft, and no way to send a technician to fix a mistake. And because of the sheer distance involved, engineers cannot simply watch and react in real time either. A command sent to Voyager 2 currently takes roughly 19.5 hours to arrive, and any response the spacecraft sends back takes another 19.5 hours to return to Earth. A single round-trip check confirming that a shutdown command was received and executed correctly takes close to a full day and a half from start to finish. If anything goes wrong during that window, there's no way to intervene until the next signal arrives, sometimes almost 2 days later. This is not a hypothetical concern. Voyager 1 has already demonstrated exactly how badly things can go wrong, even during routine operations. In November 2023, the spacecraft suddenly began transmitting data that made no sense at all. A steady stream of signal that engineers eventually traced to a single corrupted chip inside its flight data subsystem, the onboard computer, responsible for packaging science and engineering data before transmission. A small portion of that chip's memory had failed, and with it, part of the code needed to format outgoing data correctly. NASA could not replace the damaged hardware, obviously, since no human being will ever physically touch Voyager 1 again. Instead, engineers spent months carefully rewriting and relocating the affected code into other unused sections of memory elsewhere on the same computer, testing each change with waits of nearly 2 days between every single command, before finally restoring normal communication in the spring of 2024. Then, in October of that same year, Voyager 1 unexpectedly switched off its primary transmitter entirely and began broadcasting instead on a weaker backup frequency that had not been used for communication in decades, forcing engineers into yet another delicate long-distance recovery. Each of these incidents adds another layer of caution to how the team approaches every new command they send, including the one that will eventually silence Voyager 2's Cosmic Ray Subsystem for good. That enormous communication delay is also why NASA has been treating every remaining instrument shutdown with such extraordinary caution, and why the team has spent months developing a separate, even riskier plan, nicknamed internally the Big Bang, an attempt to rearrange several of the spacecraft's remaining electrical systems at once in order to free up enough power to potentially delay some of these shutdowns, or even restore an instrument that had already been switched off. That procedure was tested first on Voyager 2 in May and June of 2026, specifically because Voyager 2 sits slightly closer to Earth and has marginally more power available than its twin, making it the safer of the two spacecraft to experiment on. If the results held up, NASA planned to attempt a similar procedure on Voyager 1 no earlier than July of 2026. But even if that plan succeeds, it does not eliminate the need for the Cosmic Ray Subsystem shutdown on Voyager 2. It can only buy a limited amount of additional time elsewhere in the system. It is important to understand what this shutdown does not mean. It does not mean Voyager 2 itself is dying, or that NASA is ending the mission. Both spacecraft will continue operating their two remaining instruments, and NASA's official projections suggest that at least one science instrument on each Voyager could realistically continue functioning into the 2030s. But every single shutdown narrows the path forward a little further. Once the Cosmic Ray Subsystem goes dark on Voyager 2, both spacecraft will be down to exactly the same two instruments, the magnetometer and the plasma wave subsystem. After that point, there are no more easy trade-offs left to make. The next round of decisions, whenever it comes, will mean choosing between the very last two tools humanity has for directly sensing the region of space beyond our own solar system. There is something genuinely sobering about the specific timing of all this. Voyager 2's Cosmic Ray Subsystem has been running continuously since 1977, through the flybys of Jupiter, Saturn, Uranus, and Neptune, through the crossing of the heliopause in 2018, and through nearly 8 additional years of interstellar measurements afterward. By the time it is finally switched off, it will have operated for very close to half a century without any possibility of physical repair or replacement, a lifespan far beyond anything its original designers could have reasonably predicted. Patrick Cohen, the Voyager program scientist at NASA, has pointed out that everything the mission has accomplished since completing its original planetary flybys counts as bonus science, additional data that nobody expected to receive at all, made possible only by engineering that has held together for decades, far beyond its intended lifetime. Linda Spilker, the Voyager project scientist at JPL, has described the situation in terms that capture both the achievement and the underlying urgency at the same time. Every minute of every day, she has said, the Voyagers are exploring a region of space where no spacecraft has ever gone before, which also means that every single day could genuinely be their last. But she has also pointed out that any one of those remaining days could still bring another interstellar revelation, another piece of scientific data that nothing else in the solar system is capable of providing. That tension between celebrating an extraordinary, still ongoing achievement and quietly preparing for its eventual end sits at the center of almost every decision the Voyager team makes now. What makes the Cosmic Ray Subsystem story particularly striking is how directly its data shaped our basic understanding of where our solar system actually ends. Before Voyager 1 and Voyager 2 physically crossed the heliopause, scientists had only theoretical models predicting what that boundary might look like, built from indirect observations and educated guesswork about how the solar wind should behave as it collided with the surrounding galaxy. The Cosmic Ray Subsystem turned that theory into direct physical measurement twice, on 2 separate spacecraft in 2 different regions of space. It confirmed that the boundary was real, that it could be crossed, and that on the other side of it, the balance between particles from our own sun and particles from the wider galaxy flips dramatically and permanently. That is not a small footnote in the history of astronomy. It is one of the primary reasons humanity can currently say, with real scientific confidence, that we know approximately where our solar system ends and the rest of the galaxy begins. Once Voyager 2's Cosmic Ray Subsystem goes silent, that particular kind of direct evidence stops arriving from its side of the solar system entirely. Voyager 1's own Cosmic Ray Subsystem is already gone, switched off back in February 2025. After Voyager 2's shutdown, no operational spacecraft anywhere will still be actively measuring cosmic ray flux from beyond the heliopause. Future missions may eventually be designed and launched to study the same boundary again, but reaching a comparable distance takes decades under current propulsion technology, and no such mission is currently close to launch, let alone close to arriving. Whatever gap opens up in scientific data during that stretch of missing years cannot simply be filled in later. It will remain a permanent hole in humanity's continuous record of the boundary between our solar system and everything beyond it. For now, the countdown continues quietly, mostly unnoticed outside of specialist circles, a command being prepared, tested, and reviewed by a small team of engineers working with documentation, software, and institutional memory that, in some cases, predates their own careers. When the moment finally comes, there will be no dramatic countdown, no live broadcast, and likely no immediate public announcement beyond a short technical statement on a NASA webpage. A signal will be sent outward from one of the giant dish antennas belonging to NASA's Deep Space Network. It will cross the orbit of Mars in minutes, pass beyond Jupiter and Saturn, continue past Uranus and Neptune, and keep traveling through nearly a full day of empty darkness before finally reaching Voyager 2, more than 13 billion miles from the antenna that sent it. Somewhere inside a spacecraft built when disco was still on the radio and pocket calculators were considered advanced technology, a switch will flip, a small remaining draw of electricity will disappear, and an instrument that helped humanity mark the true edge of its own solar system will fall permanently silent, roughly 19 and a half hours before anyone on Earth even learns that it happened. If you want more real stories from the true edges of what science actually understands about our solar system, subscribe and stay with us, because every remaining signal from Voyager 2 could be one of the last of its kind that humanity will ever receive.